Very warm welcome to this highly auspicious occasion. My introduction goes with music, so it shows the auspiciousness of this occasion. We're really very pleasured by your presence at this National Research Foundation Science for Society lecture, and this particular one, Nobel-inspired. Great acknowledgement to the co-hosting of this lecture with the National Research Foundation, and specifically by the University of Pretoria and the High Commission of Canada in South Africa. And their leaders will be introduced in a moment. It is so auspicious, colleagues, not only because we have a great scientific leader and scholar, but also because of the very nature of what the Science for Society lectures are that the NRF supports. And these are prestigious national events that does not only recognize excellence in scholarship and leadership, but also engages this aspect or the construct of science for and with society. And Dr. de Mons will speak to that in a moment. We really acknowledge the CEO of the National Research Foundation, who is hosting this event, Dr. Fulu Fellow Nelmawando. And of course, the High Commissioner of Canada, His Excellency Chris Kuta, and we're very grateful for your presence here. The Vice-Chancellor and Principal of the University of Pretoria, Professor Tawana Kupe, will join us a little later, but we of course also acknowledge him in the co-hosting of this auspicious event. The Nobel process, colleagues, are upon us, and we have a live, living, active, major leader in the world. We also acknowledge, of course, our Nobel lecture series that will start officially in October when that formal process kicks off again. We want to acknowledge a number of people who's participating with us today, and specifically the newer and not so newer. So from the Canadian High Commission, Alan Edwards and Caroline Baldock, from the Trade Commission, and Caroline, of course, is relatively newly arrived, but also responsible for the science portfolio. And you'll hear remarks today about the outstanding engagement collaboration between South Africa and Canada in science. Veni Pillay is representing the Department of Science and Innovation of South Africa. She's Chief Director. And of course, we must acknowledge the wonderful program that Dr. McDonald has been engaged with and will also as part of his visit. Of course, the kickoff was last week, where he was the principal speaker at the International Nuclear Physics Conference, proudly co-hosted by the National Research Foundation's ITEMBA Labs for accelerator-based sciences. It is also within the context, colleagues, of this being the International Year of Basic Sciences for Sustainable Development. And if we think of our challenges in the country, if we think of what science is and can and must do, it is greatly acknowledged. Dr. McDonald this morning took part in an open discussion with academics of the Gauteng Physics Group, including young scientists, and will later in his program engage with a number of schools to advance this discussion about science and science with and for society, and especially with a very young generation. And I want to acknowledge at this stage, of course, the excellent work by the NRF's Agency for Science and Technology Advancement. And of course, later we will be joined by its Managing Director, Dr. Mamulethu Musia. And we also acknowledge, of course, the facilitation for the school's engagements by Michael Ellis and Maloko Malata. Colleagues, I want to introduce our key speakers, but I also need to make a little tongue-in-the-cheek remark of Dr. McDonald's excellent participation last week in the conference. With the video footage that we have seen of him and his fantastic partner, Janet, on the dance floor, you can easily give up your day job. So we're very pleased that you've enjoyed the process and the visit in South Africa thus far, and really we're delighted to welcome you. Final remark, there's a large number of online participants that are watching and engaging with us today, and we also welcome then this relatively large combined audience of this auspicious occasion. Without further ado, and in order, I would like to ask Dr. Fulufelu Nalmawandu, the Chief Executive Officer of South Africa's National Research Foundation, to make opening remarks, followed then by Chris Cooter, High Commissioner of Canada to South Africa. Gentlemen, you're welcome.
Thank you, Aldo, and good morning, colleagues. Let me repeat, good morning, colleagues. Thank you, that sounds like it. Let me start by acknowledging, and I won't repeat what Aldo has said, but maybe for completeness, His Excellency, Chris Cooter, the Canadian High Commissioner to South Africa. Let me also acknowledge Professor Tawana Kupe in his absence. I'm sure he's going to be joining us shortly. And of course, our esteemed and honored guest, Dr. McDonald and his wife, Ms. McDonald. Let me acknowledge your presence here. And of course, the prominent representatives from the networks and the global organizations, and all of you, friends and colleagues. Let me welcome you to this Science for Society lecture. We're very delighted to host this prominent event in collaboration with the University of Pretoria and the High Commission, the Canadian High Commission in South Africa. Your Excellency and Prof. Kupe, thank you indeed for making this possible. The National Research Foundation is very excited to be part of a growing science network that contributes and enables the development of locally relevant solutions. I have to emphasize that aspect, colleagues, locally relevant solutions. This is enabled through highly strategic and active partnerships. And of course, the long-standing and very supportive partnership with Canada is a flagship example of such partnerships that we talk of. The High Commissioner will further expand on some of these examples of the kind of programs that we have worked with in our partnership with the Canadian High Commission. I would like to share some selected thoughts on the significant dimensions that are shaping the global partnerships, many of which will also relate to Dr. McDonald's pathway to his success and the indicators of a global contribution to science excellence. The first one, and these are three dimensions that I would just want to tap to. The first one is the aspect of science in society and science with society. There's no doubt, colleagues, in my mind that science with society will continue to play a critical transformative role in our future. Despite our scientific progress, the developing world still has a lot of challenges, which I think a number of you are aware of. We're grappling with challenges of poverty, unemployment, inequality, rising food prices, and the list goes on and on. Some of these challenges have moved from being developing world challenges to challenges that I think affect the whole world in general. And I think it now makes more sense for us to then work in partnerships, and this is the reason why aspects of partnerships are now critical for us to then drive solutions together as opposed to working in silos, because our problems are no longer our own problems, and first world problems are not longer first world problems. When we have disaster issues of climate change, they affect all of us equally. It's a question of how do we then work together in addressing those issues. Even though Africa continues to be a huge consumer of knowledge products, there are some elements that need attention, and I just want to touch on this briefly. So the continent ranks among the least in both production of knowledge and in the spending aspects of in science and technology and innovation. For instance, we account as the continent to about 2% of the world research output. 2%, and we're talking about a continent that has over 1 billion people. That's a small number. We also spend about 1.3% of the world research spend, which is quite small as well. And about 0.2% of the patents worldwide are generated in the continent. So we have a lot of work to do. Of course, this is also coupled with a low number of skilled workforce which we have in the continent. And therefore, it is clear that we need to collectively join efforts to change this narrative. However, there are some positives. Since the transition to democracy in 1994 for South Africa, we have shown great strides in developing our national system of innovation. The investments in research and development has resulted in the country's relatively high number of researchers and a lot of research outputs and innovation products that we can see. I have to emphasize the point that much more still needs to be done. The second dimension is the issue around fundamental research. As you are aware, many pressing challenges and priorities and ongoing trends towards knowledge-based economies have seen increased pressure for science and research to demonstrate accountability through innovation and making sure that there's a return on investment. So we see this as something that is more of an investment, and once you invest in something, you must then have a return on investment. And this is despite the vast evidence of science impact in our day-to-day lives. Colleagues, this entails the need to strengthen the interface between science and society, and increasingly the role of public understanding of science and the process and impact of science. How do we educate the public to work with us? It must be made clear that innovation and socio-economic benefits of science in many instances arise from long-term continuous investments in fundamental science. And that includes physics, which we are honored to have this lecture today in the physics space. As noted by the Global Research Council, innovation is an interplay between a diverse array of participants, ideas, and resources within the complex systems that are interdependent and that are, of course, non-linear. The lecture today will further affirm this statement. The third dimension, which is my last dimension, is partnerships, and I touched on this earlier. But the growing science, technology, and innovation network will increasingly play a key role in facilitation of research collaboration. These collaborations and other partnerships are heavily anchored on a common understanding and mutual trust and transparency in order to effectively deliver on the collaboration outcomes. Trust, key pillar, and transparency. But the key aspect, again, is for all of us to remember that this is collaboration that has to be meaningful because we are solving similar problems worldwide, and we have to find ways of making sure that we work together in a meaningful form. And these networks and partnerships are going to keep us in good state. It is very important to develop and implement collaborative programs with a mixture of funding mechanisms from public, private, and development partners from the Global North and the Global South, as I've mentioned earlier, and initiatives such as the Science Granting Council Initiative, which is a multi-partner, multi-institutional initiative, presents an innovative modality of partnership between the Global North and the Global South, which the NRF is very proud to be a founding member or founding partner. I would like to express my appreciation for Canada's commitment to our long-standing partnership that continues to enable South Africa's affirmation to build better society through research and skills development. Our relationship has indeed shown the value and impact of mutual partnership, as evident from the excellent and dedicated suite of programs between South Africa and Canada, which I'm sure we are still going to have more coming down the line. In conclusion, colleagues, let me take this opportunity to again thank the University of Pretoria and the leadership of the university through the Vice Chancellor, Professor Kupe, and Dr. Heckman for hosting this event and for the partnership with the Canadian High Commission. Let me thank you all for the participation, and I'm sure, like me, we are all looking forward to the lecture. Thank you.
Professor Nelomondo and Vice Chancellor Kupe will be joining us soon, friends and colleagues. It's my great honor today to introduce you to Canada's Dr. Art McDonald, a globally recognized particle physicist and winner of the 2015 Nobel Prize in Physics, which recognized his work as discoverer of neutrino oscillations, which showed that neutrinos have mass. And let me also extend a warm South African welcome to Janet, who speaks that other universal language of music. Colleagues, when we think of the Nobel Prize, South Africa actually immediately comes to mind. 4 South Africans, including the late Archbishop Desmond Tutu and President Mandela, were awarded the Nobel Peace Prize, which I think is probably the world's highest number for any one country. But South Africa also punches well above its weight in the other fields for which the prize is awarded, having won 11 prizes in total, with laureates in medicine, in chemistry, and in literature. Like the rest of the world, Canada, which ranks number 8, by the way, in terms of total prizes awarded, recognizes Nobel as representing the highest tier of excellence. And the prize is perhaps most prestigious in the extremely demanding field of physics, where laureates are famously required to have their discoveries tested by time. And that's the background to why we're so pleased that Dr. McDonald is with us this week, because his visit, it tangibly demonstrates the high regard that Canada and Canadians, including those at the pinnacle of science and innovation, have for South African scientific achievement. I'm certain that the visit will add momentum to the already fast developing partnership that we have with you and that we are building in research and science. But let me illustrate a little bit by what I mean by that. And I have to say this acceleration and this momentum has been growing quite rapidly, even in the last few weeks and months. So I think many of you are familiar with the IDRC, Canada's International Development Research Centre. There was a period right after the end of apartheid where IDRC was extremely active, and they remain very active here, conducting research in many, many fields, social and scientific, in areas like climate change. More recently, IDRC has developed a close working relationship with the NRF, and the two organizations, for example, have established the OR Tambo Africa Research Chairs Initiative to enhance the African research landscape. IDRC was also instrumental in establishing the African Institute for Mathematical Science, AIMS. And AIMS seeks to attract the top talent across Africa in STEM. And its Next Einstein initiative recognizes the emerging talent that will originate from Africa, the country or the continent with the youngest population and the greatest need for these kind of initiatives, as the professor has said. Among more recent steps forward is an agreement between your Department of Science and Innovation, DSI, and Canada's equivalent, the Department of Innovation, Science and Economic Development, or ICID. And that's led to a very, very productive working relationship, which will be deepened in Cape Town this December at the World Science Forum. We have another recent agreement. It's between the NRF and Canada's MyTax, and that provides funding and training for PhD students and postdoctoral fellows, and assists in their recruitment for joint industrial internships and research collaborations. And I hope by saying this here, some of you will be induced to apply for that. We've also started to work, and this is a very exciting new venture, we've also started to work with Canadian and South African universities to establish a new and comprehensive network that will reinforce research ties. And we're very hopeful that our funding agencies, that all-important funding, are going to be able to support things like a joint research agenda between Canadian and South African institutions. Now, as I mentioned, Dr. McDonald is a physicist, but with a keen interest in astronomy as well. And he's held for many years, for example, the Gray Chair in Particle Astrophysics at his home base, which is Queen's University in Kingston, Ontario, along with his leadership of the Sudbury Neutrino Observatory, the SNO, which is, I'm sure, not coincidentally named that since it's in northern Canada, SNO scientific collaboration, and his ongoing research into neutrinos and dark matter. And of course, he's associated with the center in the Perimeter Institute in Waterloo. As such, in one sense, it's no surprise that he's visiting South Africa, which is becoming home to the world's largest radio telescope, the Square Kilometre Array. Canadian scientists have been involved since the outset of this magnificent project, which ranks with the James Webb Telescope as among the most important big science projects in the world. And we hope, as a government, the Government of Canada, to make a significant national contribution to the SKA, taking into account the need for this project to help the local population, and I understand that 90% of those who work there are in fact from the local community, taking that into account, as well as its impact on South Africa and global science. Now, sustainability is a core theme of our science collaboration. And climate science is another area where we are accelerating that cooperation. As we head to COP27 in a few weeks' time in Egypt, I'm confident that Canada will be increasing its cooperation with South Africa in tangible ways as your country embarks on its just energy transition, the JET, away from coal-fired electricity generation towards more generation, I hope, given what we've seen lately with Eskom. As a polar country, we're also delighted that DSI and Polar Canada, which is a government agency, have been working together on Antarctic issues. And we were very proud, as another example of our scientific collaboration, we were very proud in 2021 when the University of Toronto researchers were jointly responsible for an announcement that Wonderwerk Cave here in South Africa represented the oldest human habitation, 1.8 million years on this whole planet. Ocean science also matters increasingly to both our countries, which each have an extensive marine area of jurisdiction. The recent visit of our Minister of Fisheries and Oceans with your Minister of Environment highlighted our shared objectives on stronger oceans management. In December, Canada will host in Montreal the UN Biodiversity Conference, COP15. We as a country are committed to the goal of 30% of land and 30% of marine areas protected by 2030, the so-called 30-30 by 30 initiative. And I'm certain that with South Africa, we can find ways to advance global commitment to much greater protection of the increasingly endangered life on this planet. Now, as the number of Nobel Prizes in medicine awarded to South Africa highlights, not to mention, of course, the world's first heart transplant, South Africa has an astounding record in the field of health science. With the COVID pandemic, solid health science has become more important than ever. And Dr. McDonald himself in 2020 and 21 was the Canadian lead on a project that has delivered more than 7,000 low-cost ventilators. Recognizing that South African science played an especially important role in the pandemic, including being the first in identifying 2 of the 4 COVID strains, itself a reflection of the deep expertise in virology built up during the long and the grueling HIV/AIDS crisis, Canada was quick to support the establishment in Cape Town of the new mRNA vaccine hub. We're the second largest donor to this cutting-edge facility, which will help to coordinate the application of the new mRNA technology to combat not just COVID, but many, many diseases that are endemic in Africa and elsewhere. And that technology will be transferred to developing economies, helping to make access to life-saving vaccines much more equitable. As you know, Canada has a feminist foreign and development policy. In fact, ensuring gender equity is a core objective that runs through all our policies, both at home and abroad, from security to trade to UN initiatives. We've made progress, but there is far to go. In particular, we must do more to enable women and girls to enter and to excel in the STEM area. It's crucial we bring women fully into this field, essential as it is, as the professor was saying, to the transition of our economy, what you call in South Africa the 4th Industrial Revolution. It's essential to our society as well that women are full participants. So through all of our efforts in science and research cooperation, including those with South Africa, Canada will be committed to closing that gap, so that women as well as men achieve the highest levels of success in science, technology, engineering, and maths. Let me conclude by reiterating that we are honored by Dr. McDonald's presence, but also genuinely excited by what his visit represents. I think it represents the start of a new era in our people-to-people and our institutional ties across all fields of science, research, and education. A very big thank you to the Vice-Chancellor, who will be joining us soon, and to Future Africa, this groundbreaking new institution, which has graciously provided a platform for us today. Let me thank my staff for their work as well. And last but not least, of course, let me thank the National Research Foundation, whose Science for Society lecture series has made this event possible. Over to you, Dr. McDonald.
Well, thank you very much. I'm really honored to be here today to speak with you. And Janet and I have really enjoyed our time in South Africa, in Cape Town first, and at a wonderful conference emphasizing the capabilities of South Africa in nuclear physics. This is a major conference that only takes place every 3 years. And it was hosted by the ITHEMBA labs, which I had the privilege of visiting, where they were opening a new accelerator for isotope production, an indication of how basic science can lead to very valuable things for society. I also visited Ames and spoke there. I have a personal interest in it because I'm a personal friend of Neil Turok, who comes from South Africa and who championed the cause of this set of Ames Institutes, which I think are now in 5 countries across Africa, and had a chance to talk with the students and see the future of African science and mathematical capabilities. So, Road to the Nobel I was given as a topic for today, and so I chose to say a little bit about how anybody from anywhere can end up, if they have the right circumstances, and I regard myself as being very fortunate as having been able to follow a path that enabled me to end up with a Nobel Prize. Principal among those things is the fact that when students ask me, how do you do well in science, I say, choose your collaborators well, because I received a Nobel Prize, but I received it on behalf of 200 to 300 scientists and technical people who actually did the work on this major experiment I'm going to describe to you. And I'm simply representing them here as a Nobel Prize winner. But let me start with where I came from. It's a small place in Canada, Sydney, Nova Scotia. I and my wife, in fact, are descendants of very early settlers in Canada, going back, I think, 7 generations in my case. It was a working class environment based on the steel industry. You can see that it's really in the far eastern part of Canada, and I've been really enjoying the seafood I've had here in South Africa. Takes me back to my childhood days. And I went from Sydney to Dalhousie University, also in Nova Scotia, for my undergraduate work. There's a picture of Cape Breton in the unspoiled areas. It's really quite a tourist attraction. And on the right is what is not a tourist attraction, and that is the way the city was in the 1960s when Janet and I were in school there. It was a very industrially oriented town, but then education was emphasized, and as is often the case, teachers are very influential in people's success. My high school math teacher, Bob Chafe, gave us extra classes after school in mathematics, and in the class of 35 out of a total graduating class of perhaps 120, there are 2 PhDs in math and 1 in physics from that particular year. Just an indication of this gentleman's skill. I went to Dalhousie and I discovered physics. I went there knowing that I loved math and I wanted to apply it in some way. And in fact, the other thing I often say to young people is who ask me, how do you choose a career? I say, well, think about the things you might like to do when you get up in the morning. And I knew that was going to be something that involved math in one way or another. But then try a variety of things and see what you're good at. And lo and behold, when I tried physics, and I was good at it. And so I put the two together. And if you do that, put it together, you'll have fun every day and you'll also be successful. So that's what happened with me. And I discovered that physics really enables you to understand the universe at all levels, from the most microscopic to the farthest reaches. And in fact, that's what I'm still doing, and that's what I'm going to talk to you about today. Now, I was very fortunate, and this is an indication of the value of international cooperation in education. I was very fortunate in being able to go to graduate school at California Institute of Technology in Pasadena, California. I had professors, I was saying this morning to the physics students. Richard Feynman was the person who taught me quantum mechanics in physics, a legendary Nobel Prize winner. And the head of the laboratory I worked in, William Fowler, but no one would ever call him William. Willie was his name, and he got the Nobel Prize for figuring out all the nuclear reactions that power the sun, and generate, in fact, what we're made of: hydrogen, nitrogen, carbon, oxygen. It all comes from generation in stars by these reactions. The start of what was original what was some of the original neutrino measurements, in this case neutrinos from the sun, was happening there in the late 1960s when I was a student there. A combination of experiment and theory. It happens, in fact, that here in Africa, initial measurements of neutrinos in underground mines was happening as well in the 1960s. I'll show you that towards the end of the talk. So I worked on a little bit on these experiments of how you understand how the sun burns, but also I worked on fundamental physics measurements using the nucleus as a laboratory. I then went to Chalk River in Canada, somewhat similar to Itemba Labs. I went on to a full professorship at Princeton and co-director of their cyclotron laboratory. And then in 1984, I was one of the 16 founding members of the Sudbury Neutrino Observatory collaboration. And we started in 1984. Our results for which the Nobel was awarded were in 2002. And so this was an extremely dedicated group of people. In the process, we educated over 200 students and postdocs. And those students and postdocs, we did a survey later, only about 25% of them ended up as academic people, professors in universities. And I'm very pleased to be able to say that over 35% of the people who have those academic positions are women. That's not common in physics these days, and I consider it to be progress. The other 75%, we did a survey 10 years after the project was over. They work in a wide variety of occupations. The commonality is evidence-based decision-making, which you want in everything if you're going to have sensible decisions. You want it in industry, you want it in government, you want it in science, of course, where it's the central element of it. And so whereas we were training students in basic science, and we actually attracted some of the very best students, they went on to work in society in a wide variety of areas. And that's a part of the theme of what we're talking about today. So I moved back to Queens in 1989 as the director of this large project. This shows you the group of us in 1986, and the guy on the right who doesn't have white hair at that time is me. The founders were Herb Chen and George Ewan. Herb Chen actually comes from the University of California at Irvine, which is where Fred Reines, the professor who did those neutrino experiments here in South Africa, pioneering experiments in the Rand mine here, came from. And so the history of neutrino physics, and we'll now talk about these things called neutrinos, which are not a breakfast cereal, actually, although sometimes they're confused. Along with electrons and quarks, they're the basic particles that we don't know how to subdivide any further. We always say, so far, we don't know how to subdivide them any further. They come in three flavors, electron, muon, and tau. We call them flavors, although you don't taste them. You, with great difficulty, attempt to detect them, see their presence. They only feel the weak force they don't feel the strong or electromagnetic force. They can pass through an amount of lead equivalent to the distance that light travels in a year, 10 million billion kilometers of lead, with only a 50% chance of hitting something, because they only stop if they hit the nucleus of an atom or the electron going around it head on. And so it's very difficult to detect them, but on the other hand, you can get them out from the core of the sun through that dense material, and there are enormous numbers produced in the sun. In fact, right now, for every square centimeter of your body, if you hold out your thumbnail, in the next second, there will be 5 billion of the neutrinos, 5 million of the neutrinos of the same type we detected going through through every square centimeter of your body. But only once in your lifetime will a neutrino stop, and you won't even notice it. It'll change one atom into something else, but only if it happens to hit you in the eyeball, and if your eye happens to be closed, as many eyes often are by the time I get to this point in my talks. If that were to be the case, you might see a little burst of light. Otherwise, you're not going to notice. And so they're hard to detect, and so we had to build a detector the size of a 10-story building in order to detect 1 an hour from the sun. And we had to restrict all the other forms of radioactivity in the vicinity that might also produce little bursts of light. And particularly, we had to avoid the cosmic rays. The reason we were interested in it is that there was a puzzle with respect to neutrinos coming from the sun. There were too few being observed compared to theory. We didn't know if that was because we didn't know how to calculate the reactions that are powering the sun, which itself would be a problem, or because there's something outside of what had come to be known as the standard model of elementary particle physics. So we went, no, the wrong way, we set out to get an answer to this question, set out in 1984. At that point, there was this one experiment that had shown this effect, and either the calculations were wrong or the experiment was wrong, or the electron neutrinos, which is the only type produced in the sun, were changing into another flavor, and that would elude the other experiments. But with material called heavy water, deuterium oxide instead of hydrogen oxide, an extra neutron in each hydrogen atom, which it turns out there's a fair amount of in Canada. It's very expensive to produce, but it's used in the Canadian style of nuclear reactor, which doesn't use enriched uranium. It uses natural uranium, but controls the neutron flux to maintain the chain reaction. So Canada had reserves of this. And so we were able to, by great foresight, from our perspective, great foresight by people in the government who had control of these reserves, we were able to borrow 1,000 tons of heavy water, which at the time was valued at about $300 million. We had to pay about $1 million a year in insurance in order to put it in an acrylic vessel 2 kilometers down in the mine, which is where we chose to do the experiment. And we were able to do that experiment because there was a mining company which is still running that mine with 5,000 tons of ore, nickel ore, coming out every day from the same mine shaft, which you can see here on the upper left here. This mine shaft is the same one that we use to go down to that red dot, which is where our detector is. And they use it for taking the miners down, and the other side of the shaft, they take the ore out. But for us, it was a tremendous advantage that they were allowing us to work at this level. They're now mining several thousand feet below where we are, where our detector is situated, because they keep the mine in great shape. Safety is number one, and we coexist with them. So the idea here is that you take this, get the spotlight working here, you take this heavy water, you put it in an acrylic sphere in the center of the detector. That acrylic sphere had to be built out of 120 pieces bonded together underground. That acrylic sphere holding the heavy water is surrounded by 10,000 light sensors, you can see in the sort of geodesic structure. And outside that, there's ordinary water, although highly purified, in a container that is keeping the radon from the walls from getting into the detector, because radon is a radioactive substance we are trying to avoid. By going 2 kilometers underground, we had a detector which avoids cosmic rays, and cosmic rays do that. Have any of you, maybe the Canadian Embassy or High Commission people, have seen northern lights? But in South Africa, for obvious reasons, you don't see northern lights. This is what happens in the atmosphere in Canada from cosmic rays impacting and brought into the northern hemisphere by the magnetic fields and making the atmosphere glow. When you're looking for one faint burst of light per hour, you can see that you need the factor of 1 million or more reduction in these cosmic rays in order for you to be able to do your experiment. And we were very fortunate in having a mine management that would allow us to do that. In addition to that, we had to avoid any local radioactivity that might produce bursts of light in our detector. And so everybody who came down to work on this took a shower and put on lint-free clothing, something like 70,000 showers in the process of manufacturing this detector. You can see here on the right the manufacturing of the acrylic sphere from the 120 pieces. You can see the light sensors being installed in a sequential way. And here, all the cables are in place going to our computers and enabling us to collect the data. So this is what we're talking about. A couple of nuclei come together in the sun. They produce a neutrino, which heads through the solar system. This one happens to be going to Sudbury. When it comes to Sudbury, it goes underground, past our buildings on the surface, past the workings of the mine, and it reaches our detector. At that point, it produces a burst of light. If it's an electron neutrino, it produces one type of burst of light. If it's a muon tau or electron, all three of them can break deuterium apart, making a free neutron in the heavy water, and we can observe that differently. And so what we're able to do is compare how many explicitly electron neutrinos, which is the red that you see on the right here. Oops, go back. The red here is the fraction of the neutrinos from the sun which were predicted. If you look at the overall scale, this is the number of neutrinos per centimeter squared per second, about 5 million. The hatched line is the level that is calculated. The electron neutrinos that we saw from the first reaction are only about a third of the total, whereas the measurement of all neutrino types matches extremely well with the predictions. And the cross-hatched light blue are the muon and tau neutrinos into which the electron neutrinos have changed. By 2002, starting in 1999, we had enough statistical accuracy to be able to say that there's a less than 1 chance in 10 million that electron neutrinos were not changing into the other types. And that was the significant discovery. 5 standard deviations is the term that's used in particle physics. But in addition to that, note that the total number of neutrinos is in excellent agreement with the solar model calculations, which means we know how to calculate very accurately fusion reactions, nuclear fusion reactions, in a very extreme condition. This hot plasma is held in place by gravity in the sun. Here on Earth, we are attempting to develop fusion power. The largest example of this is the ITER, International Tokamak Experimental Reactor in France, in which Canada is one of the partners, where they use magnetic fields to make a magnetic bottle. So these very hot plasma particles get turned around by the magnetic fields and put back into the plasma instead of scraping the walls. And therefore, it's possible for it to confine it. And if it is, in fact, capable of doing this, and this will be the first example of more power out than power in the case of the particular ITER facility, then you have an almost unlimited source of fuel. That same heavy water I was talking about, 1 in 6,000 of the molecules of water you drink is the type of fuel that you could use in the long-term future for fusion power. So it's an example of how basic science that we were attempting to do provides confirmation of calculations that are essential for what could be a very clean and effective source of energy in the longer term for humankind. So here is the set of things that resulted from our measurements with snow. We proved the neutrinos change from one type to another. And we proved that they have a finite mass. Those two things go together in the physics of it. We proved that fusion power is calculated very accurately. And we also proved that neutrinos are not the dark matter that has become a significant interest at present times, At the time we started the experiments, neutrinos could have been the dark matter that holds our galaxy in its present form. And that led to the establishment of SNOLAB, the laboratory that is now 3 times the excavated volume of the original SNO detector, where dark matter is one of the main objectives of the experiments. So now we'll talk about wrong Big Bang Theory. I'm going to talk about the Big Bang Theory, but just to go back for a moment, one of the perks that you sometimes get with this Nobel Prize thing is an opportunity to do something that's really fun. And it turns out that the technical advisor for the original Big Bang Theory was a former student of mine at Princeton. He worked for us in the summers in Princeton when he was studying there. He's a professor at UCLA. And so I and my son, who happens to be involved in film post-production, and his wife managed to go and be Geek of the Week at a filming of the Big Bang Theory, which was great fun. But the real Big Bang Theory has been fleshed out in much more detail in the last, let's say, 30 years than it was before that. We now think that the way in which the universe has evolved is that about 13.5 billion years ago, there was an enormous expansion caused by what you might consider an enormous explosion. And after a very short period of time, that conversion of energy into matter and equal amounts of antimatter produced all of the particles we know about, neutrinos, electrons, quarks, and their antiparticles. But somehow, our universe is just composed of matter. We know and we've identified antimatter particles corresponding to all the particles that make things up, but we don't know where they have gone. And there's a process that we're studying called neutrinoless double beta decay, to which we have converted the SNO experiment, that can give us some of the information as to how that happens. So as you go on in time, when you move to about a microsecond or so, you find the quarks coalescing to form the nucleus of atoms, and then shortly thereafter, the nuclei begin to form into, the quarks at a microsecond form neutrons and protons. Quarks are the interior part of a neutron or proton. They combine to form the nucleus of an atom after about 3 minutes, and after 30,000 years, you suddenly get transparency because electrons add to those nuclei, forming neutral atoms. That's the point at which you get what's called the cosmic microwave background, which has been studied in minute detail, and which gives us a lot of information about how the universe has evolved and how it is composed. I'll say a little bit more about that later. At this point, which is about 1 billion years after the original Big Bang, or something like 12 billion years back from today, you start to have galaxies form. The first galaxies formed from the hydrogen that was the original material, we think, that formed at the time that atoms formed in the 300,000 year period. This is the period where the square kilometer array will have its most advantageous opportunities to give us new information. And the ability with this new telescope situated here in Africa, for which you have a natural advantage of the site and the strong international cooperation, is going to enable us to understand this period in our evolution when the very first galaxies and stars are forming. Now, there is this material called dark matter that appears to make up about 26% of the total, about 5 times more mass than us, than the type of matter that we are formed from and the type that stars are formed from. Here's the current summary of what we understand. Matter is about 4%. ordinary matter we call it, dark matter, which is dark. If you look out on a starry night, the material between the stars is about 5 times as much mass as what there is in the stars, and that's the dark matter we're talking about. There's also something called dark energy, which is it's a way of describing something that has been observed, which is that gravity is not always an attractive force. There's a small component that is repulsive. It was in Einstein's original general relativity, but he put it in for a different reason. Now, at SNOLAB, we can look for dark matter particles left over from the Big Bang. We can look at this. At the Large Hadron Collider, they're attempting to produce dark matter for the first time since the Big Bang. With the square kilometer array and other measurements, one can study both dark energy and dark matter by studying the influence on the formation of galaxies of these unknown things, dark energy and dark matter. Dark energy has been studied by and observed to occur by studying far distant supernova, for which the amount of light for a given supernova is well defined, and measuring from the redshift how fast it's moving, and putting those together and observing that our galaxy, our universe is in fact accelerating in its expansion. The easiest way, and in fact one of the first ways in which dark matter was identified, was simply by looking at a galaxy like our galaxy, and our galaxy looks like this. You don't see that from Earth. When you look out on a starry night, you see a band of stars that we call the Milky Way. That's our galaxy, but it's a pancake, and you're looking along the edge of the pancake. And actually, it's more like a cinnamon roll. And the speed of the stars in the outer regions is so high, that's the data points you see here, that if it were being held in place only by the glowing matter, it would look more like this lower curve that you see here, the one that comes down. There's an additional component that's referred to as the halo, which is this dark matter that we do not really understand. It doesn't fit anywhere in the standard model. Weakly interacting massive particles is one explanation. Scientists love to be a bit of whimsy, so WIMPs is what we're a bunch of geeks looking for WIMPs. So that's what we do with experiments in our underground location. And we're looking for these WIMPs to strike our detectors, and we have different kinds of detectors that produce different effects when struck by a dark matter particle, making a nucleus recoil. We have different materials, argon, helium, fluorine, a large set of experiments in this expansion of our laboratory. On the left, you see where the original SNO experiment was and where SNO Plus is now. On the right, you see the expansion, and you see the set of experiments that are either in place or being planned for these locations, most of them looking for dark matter with different materials. This laboratory was built with a Canadian fund to attempt to attract people from around the world to come and work with Canadians in Canada. The two others that were funded at the same time, one is a under-ocean network, an instrumentation that enables people to do studies off Vancouver, and the third is the Amundsen icebreaker, which is something that does research in the far north. And so Canada is interested in international participation, both in terms of having people come to Canada, but also in the case, for example, of the SKA, in having Canadians work internationally here in South Africa. So international science is a great way to do more than you could otherwise. This is what it looks like in this ultra-clean laboratory. The whole laboratory the air is highly filtered, very clean. And this is when we were visited by Stephen Hawking, for the second time actually. He came in the first time in 1998. Absolutely remarkable individual, inspiring to everyone that met him. He wanted to go underground. Everybody that goes underground, as I said, takes a shower. Didn't work for him. So we vacuumed him off and put him in a special mine cage so he wouldn't get more dust on him going down. He had a wonderful time. At this time, which is a little over a year before he passed away, he could only communicate by twitching his right eyebrow in order to find a word on the screen as it scrolled past. But he asked questions of our students and formulated them laboriously. Had a sense of humor when he spoke. He referred to that cosmic microwave background that I mentioned earlier on, which has cooled off now until it's about 2.7 degrees above absolute zero, something like minus 270 Celsius. He said almost as cold as Sudbury in the wintertime. So anyway, very inspiring individual. This is an example of that argon experiment I mentioned. We are now working on an even larger experiment in the Gran Sasso laboratory in Italy, 3 tons in SNOLAB, 20 tons in Gran Sasso, and ultimately 300 tons back in Canada. So with this, with taking advantage of a unique opportunity, heavy water initially, but now this deep underground site, lowest radioactivity location in the world, we can study the sun, we can study the Milky Way with dark matter, we can study the influence on, we can study dark matter, which influences the expansion of the universe. We can even study the Earth, because neutrinos make, rather, uranium and thorium make up about 40% of the heat flow out of the Earth, and we're able to study that with neutrinos down about 600 kilometers. We can study the Standard Model. This is the model that is these days considered to be the description of how things work at a most microscopic level. So we're going from the farthest reaches to the tiniest reach. Here you have quarks. What we're made of is entirely in this first generation, as it's called, up and down quarks, which combine in threes to make neutrons and protons, which then combine to make the nucleus of an atom, with electrons going around the outside. The electrons are associated with that, and electron neutrinos are associated with processes involving those electrons, including the reactions that power the sun, but also things of great value here on Earth, such as the antiparticle, for which there is an antiparticle of all of these, the positron. The antiparticle of the electron is used in positron emission tomography, where radioactivity is used to study things that are needed for diagnosis or treatment. The other particles here, the other quarks, the other neutrinos, are produced in higher energy processes, either in cosmic rays or accelerators. Higgs boson was discovered with much fanfare, and rightfully so, at the Large Hadron Collider, provides the mass mechanism for all of these particles, except for neutrinos, which is the first bit of information for physics beyond the Standard Model. And dark matter, which we know exists, but which fits nowhere in this model. And so we're able to take the whole range from the most microscopic to the largest things in the world. Now, I mentioned there muons and tau. These muon neutrinos that you see here, associated with the heavier electrons, muon electrons, muon, which are heavier versions of the electron, are what was discovered by Fred Reines in the first experiment done underground to detect neutrinos. And it was done here, as you can see, at the East Rand gold mine near Boxburg. He did it in 1966, and they observed the neutrinos that penetrated through after the other cosmic ray particles had been eliminated by the rock And this is what led eventually in the 1990s to more detailed measurements of muon neutrinos that led to the Nobel Prize for the Super Kamiokande experiment, which we shared with them, because they observed oscillation of those same muon neutrinos as they crossed the Earth. There were fewer on the other side of the Earth as a result of the oscillation. Now, it was mentioned that we developed ventilators, and this is something that everyone who worked on the project was very highly motivated and worked very hard, starting right at the beginning of the COVID pandemic, when the leader of the experiment I showed you that's being cited in Gran Sasso, he was in Milan and locked down as a result of Milan being one of the first hotspots. And I got a call from him where he said, I think the technology we're developing for handling liquid argon, all the elements of that are very similar to what you would put in a ventilator. But these days, ventilators are in short supply. The ones that are available are very sophisticated, several thousand parts in them typically, and the supply chain has just been blasted by COVID. I think we could build a simpler one using our expertise. And so we set about doing it. Ultimately, several hundred scientists worked on this project, including people from national laboratories across Canada. And we were able to get a government contract because they asked for new developments. This is a specific ventilator for people who are in the final stages of COVID. It's for intubated patients in the ICU. But it costs about 5 times less than those very sophisticated units. And the supply chain, therefore, because it's only 50 parts or so, was much less. The amount of effort to do this was substantial because it's very different to build an experiment for your own purposes and another thing altogether to build something where you're keeping someone alive. We managed to deal with all of the certifications by the end of November, started producing them, and there are now 7,000 of them in the Canadian stockpile, and the Canadian government is certainly favorable to donations to countries in need. We also made sure that it was open source. The design was published right from the very beginning, and so was the final design, so that anybody wanting to do this in another country would be capable of being able to take the design and run with it. So this is the sort of thing that shows you the residual capability that exists in the basic science community to do things that are of value for society, even though their main concentration in the work they do is to be at the frontier of their field, which is also valuable for industry. Any industry that's going to have a front-end product has got to be at the front end of the science as well as of the technology. So, observation. Anybody, including people from small working class towns, can end up with a Nobel Prize if they have the right opportunities, are educated by the right people, have really skilled colleagues, and if you can be collegial and work in a good team, you can go much further than you can do on your own. And it's the science that motivates us as scientists. It's not winning a Nobel Prize. That's very nice once you've done the science and recognized yourself that you've made an impact. This is a recognized body that gives you a recognition that's recognized around the world, but it really is a science that motivates everybody. And you can do extremely good science without winning a Nobel Prize, and people do it every day. And that's what is important. And so for young scientists, make sure that you keep up on the latest things. This was the first computer at Dalhousie University in 1964, being lifted. It was an IBM 1604, I think, being lifted through the roof of the physics building with a crane. But some things don't change. They asked myself and another undergraduate, learn Fortran and teach the professors. Because nobody in the university had ever programmed a computer before. I still learn about computing from the students as opposed to myself. And so that's how things change with time. In summary, We had a couple of natural advantages in Canada to be able to do this Nobel quality research. And here in South Africa, you have a major natural advantage with your site and also your competence within your community for doing the square kilometer array. And Canadian astronomers are excited to be partners in this major step forward for astronomy. Willie Fowler, the fellow I mentioned before, when he received the Nobel Prize, he put a motto on his written version of his talk: ad astra per ardua et per ludum, to the stars with hard work and fun. And it really was fun to work in his laboratory. And so there's no doubt, science is fun. So I should stop at this point.
Thank you indeed, Dr. McDonald. Won't you take a seat, please?
Sure.
Dr. McDonald, thank you indeed for such an inspiring and understandable lecture. I must quote you. It's nice to win a Nobel Prize, but it's the science that counts, of course. And I think that portrays not only your personality and work ethic, but your engaging approach and the excellence with what and how you have approached science. Also the elegance and the absolute simplicity that you have provided us to understand this very tremendous and challenging field, and of course the applications of what this is about. I must tell you, and not speaking for our CEO, there's due consideration that our National Research Foundation currently is giving in terms of that advancement, application, tangible aspect of the investments that we're making in basic sciences and discovery sciences, which have all, well, of course, will always stay fundamental. But I think you have shown that that application component, and of course, indeed, why the Nobel Prize was awarded to you and your collaborators in the teams, will stay important. We want to extend this discussion, colleagues, by a brief panel discussion. Please bear with us for the whole session to end at 1:15, please, and invite the panelists and the excellent moderator to come to the stage to also include Dr. McDonald in discussing aspects of enabling Nobel quality research in Africa. So firstly, please, Dr. Heide Heckman. She is the Interim Director of Future Africa, this fantastic campus that we all are gathering. She's the former CEO of the International Science Council, previously the ED of the two constituent councils for social sciences and sciences. She works to a large extent still with the United Nations, is a fellow of the ISC, and she is a social scientist. Welcome, Dr. Heckman. Our first panelist, then Professor Thulani Makalanyane, who is from the University of Pretoria, holds a DSI NRF research chair in marine microbiomics. He is the recipient of numerous prestigious awards, inter alia, and recently the very prestigious NRF P rating. Thank you very much, Thulani. And of course, Professor Mansai Deale, full professor of physics here at University of Pretoria. She holds a DSI NRF research chair in clean and green energy, highly regarded in her field, the leader in this area. You are very welcome. Colleagues, the panel was constituted specifically not to be physicists, to have a transdisciplinary approach, to have young and established scientists both, and to bring a broader discussion on the excellence of science and what does it mean to develop and support that level of science on the continent. Colleagues, you're very welcome. Dr. Heckman, please.
So I think it's easier for me to stand here. I hope that works for the colleagues at the back. I also thank you very much, Aldo. Where has he disappeared to? And Dr. McDonald, I also would like to extend my thanks to you for a fascinating lecture. As a social scientist, I particularly connect to the human story, the story of the magic of science, of scientific discovery. And I'm happy to say that I understood a lot more than I had anticipated. So that's a great compliment. Colleagues, we have restricted time for the panel discussion, and so I thought I would structure it in the following way. First, I want to give our two panelists who have joined us, Mansai and Tulani, if I may use your first names, to share with us their reflections on the 2 or 3 key take-home messages from this lecture. And then I want to pose one overarching question, which is a science policy question, but I think given that this is an NRF hosted lecture, that is relevant. And in any case, I wouldn't be able to hold my own on a more substantive question around the science. But, and then we'll get responses from all 3 of you to that overarching question. Let's see whether time permits perhaps you to ask Dr. McDonald more specific questions. So if I may start with you, Mansai, your 2 or 3 key take-home messages.
Thank you very much, National Research Foundation, University of Pretoria, and you colleagues, both in physics and just people, we work together. Science is fun. That's the message that I got very well. I've been asked this question many times by my colleagues at the NRF and the general national science landscape in South Africa. Why are you still sitting at a university? I'm doing fun work. It's exciting. What I have learned from the presentation by Professor McDonald, his name is Art, right? Right. Is he from Zimbabwe? Success, Reason, those are the names from Zimbabwe. Okay, the Earth is a spaceship, and all of us are traveling in the spaceship at that particular speed, and we are busy destroying the spaceship, but the spaceship has no place to dock for repairs, and all of us are expected to repair the spaceship whilst it's in motion. So if we learn from what Prof. McDonald has said, is that from the fundamentals of science, we will definitely need to work together from those basics to the next level of science, such that we don't forget that there's still room at the bottom, as your lecturer, Richard Feynman, has said. So for you to become the Nobel Prize winner, which is the road to being there, it's a collaborative effort. You must be prepared to work collegially with other people, please, collegially. Don't plagiarize on anything like that. And be focused. That's what I have learned. That's for all of us as scientists. And then for our funder, the National Research Foundation, is that this basic sciences is actually a very important element of the future innovations. You deliberately continue with what you are doing, then once in a while or one day you woke up and there is a need for the ventilators. It's not that you started in 8 months, it's something that has been there. You just put it together. My message, my take-home message is that don't underestimate the basics and the beginnings. And the funders and the university and all who are supporting us in research, just be there with us, even though you don't understand what we're saying. Thank you.
Thank you so much, Manta. Good. Tulani, over to you.
Thanks, Hada, for the opportunity. So Dr. McDonald, I really enjoyed your talk as well. I thought it was very illuminating. There's a lot of notes that I took down, but maybe I'll stick to two. The first one is really about the importance of collaboration. Maybe we can talk about how you actually choose some of your collaborators, because I'm sure that makes a big difference. And the second point that I had is when you spoke about taking advantage of the unique opportunity. I think this is something that applies for us here in South Africa. Within my own space, so we work in, environmentally, one of the most interesting locations on Earth. And I think this is something that we are probably not, making the most out of in terms of what we could be researching. And by doing that, that will also allow us to, over time, produce science that actually provides value to the entire globe. So that's the second takeaway that I had. And then the third one was what Manzai also talked about on the residual value of basic science. This is something that cannot be overestimated enough, because there's always a push, and I understand the reasons, especially for us being in South Africa. We have multiple challenges. We're not as advantaged as Canada. And there's always an inclination to sort of move towards the basic needs, addressing the basic needs that people have. And often there is a lack of vision as to where we want to be, a decade from now, several decades from now. So those are some of the messages that I really took away from your talk, and it was quite inspiring.
Thank you very much, Tulani. So I want to build on some of what you have both indicated as some of the takeaways to ask my science policy-oriented question, and this is aimed also, I think, at the NRF. So, in some ways, if we look at the context in which science now is under pressure, it's a world in which, people talk about cascading systemic risk, a world of inadequate responses to highly complex and urgent global sustainability challenges, a world of so-called existential threats to humanity. And the pressure that this has put on science communities, but also the responses from science policymakers and science funders, is to turn increasingly towards transdisciplinary approaches as possible pathways to accelerating the impact, the positive impact of science, and to unleashing the transformative potential of science, the potential of science to inform and support urgent social transformations that we all know are needed in order to secure just, sustainable, thriving societies all over the world. And UP is exemplary in pursuing this imperative for transdisciplinary work. And what we mean by that, of course, is breaking down silos, transdisciplinarity as an approach to research that crosses disciplinary boundaries, the boundaries between all scientific fields and disciplines, and also the boundaries between science and society. So engaging societal actors as partners in processes of co-designing and co-creating knowledge for social transformations to global sustainability. So that's all well and good, but I think the reality is that our science policy discourse still has embedded in it some dichotomies in our thinking that create potential tensions and that possibly undermine the transdisciplinary project. And those dichotomies, I think, classically are about basic versus applied research and the sort of time frame that goes with that. Long-term, curiosity-driven, immediate, action-oriented, the knowledge-action spectrum dichotomy. And what goes with that, I think, the enduring debates around excellence and impact. And the drivers of that, competition as a driver of excellence, collaboration as a potential driver of impact. So and I think some of these dichotomies or the tensions between these divides led to the International Year of Basic Sciences for Development, which is a UN year and was in fact led by the International Union for Pure and Applied Physics, IUPAP, and is now supported by all the international scientific unions and associations that are members of the International Science Council. So I would like to ask each of the panelists to reflect on how in your work and from your career and your scientific perspectives, you have encountered these dichotomies in good or negative ways, and whether you feel they are still valid and important categories to maintain, important in the sense that they can shape how policy and funders actually structure and support science for society, let's say, science with society. So I hope that makes sense to you, and I hope that it allows you to reflect a little bit more broadly on what we've heard from Dr. McDonald in terms of I think some of the examples that have been given do traverse these dichotomies, and yet I think when it comes to policy, we still maintain in our framing these essential differences. So I'm going to go from that end and end up with you, Dr. McDonald. Tulani, I'm going to start with you.
Yeah.
Can the people at the back hear us if we don't use that microphone?
Yes.
Okay.
Thanks, Haida, for that framing. Yeah, I mean, as a young academic, of course, some of the things that you bring up are challenges that a lot of us face in front of interview panels, or promotion panels, and even NRF rating panels, where you are expected to, I guess, be more grounded in your specific discipline, and interdisciplinary sort of research is something that's taken as a distinct disadvantage. But unfortunately, or maybe fortunately enough, the challenges that we have call for interdisciplinary research. And that is absolutely where research, irrespective of the specific discipline, whether social science or fundamental science, is heading towards. It's still a challenge, of course, because we are at this space where we have to face people that have those beliefs in terms of how you should be grounded in a specific discipline. But I guess having sessions like this where we kind of articulate more why it's important to have transdisciplinary research, and maybe also encouraging our institutions to move more towards not traditional academic departments where you have a department of chemistry, physics, but having departments that are centered more around questions, whether it's marine research or ocean research, that really will be something that drives all of us towards more interdisciplinary research. I hope I captured all of those.
Yeah, that's nice. And I'm reminded, I think your last comment also about that sort of mission orientation really is about a really inclusive approach that makes space for all types of science, all disciplines. Good. Mansai.
My own research is in clean and green energy. I remember the day Professor Burton was asking me, give this chair of yours a title. And I was getting confused. But I realized that we are all working on a solution, deliberate solution. In Rwanda, they say homegrown solutions of food, energy, water nexus. And that requires nothing. For us to achieve the goal, we need to be working together with all the departments that you can think about at the University of Pretoria in particular and everywhere else in the world, without excluding the community. Every one of us have, today I've heard Dr. McDonald talking about, Professor McDonald talking about Nobel Prize that was won in 1995 using our land. an experiment that was done in Boksbeek with Selchoff, Professor Selchoff. It's exciting that we can still provide the mining community some solutions. As Art has said, that they have built a laboratory underground by using a mine that is working. Actually, he says that that mine is working. It's not an old, unused mine. So I believe that we should work together. I've been asked many times with the type of topics that I work on, that what are you now doing with photosynthesis? Photosynthesis is the basics of the solar cell that I make in the lab. If you want to know the oldest solar cell in the world, go to the tree. It will tell you how to extract the sun energy. They know how to do it. And that I cannot do without a biologist. If I've not done it right, please just come and help me, a biologist. And that's how we work together. We really have to be, the term that we use, in South Africa, we speak of on the ground, deliberate. We need to be deliberate. We need to be on the ground. We need to work with each other to achieve one goal, to save the world from destruction. And in a nutshell, in a nice summary, is that you can do all the experiments that you are doing in the world. You can't do anything and win without physics. Thank you.
Thank you very much, Mansai. Dr. McDonald, what wisdom would you share with us in terms of how we overcome these, in some ways, artificial distinctions?
So, in the year 2000, Time magazine in the US chose Albert Einstein as the person of the 20th century. Not because he invented the laser or the computer or the GPS or many other things, but because the simple physics insight that he provided at the beginning of the century was the basis for essentially all of the technological development during the 20th century. It's still happening today, because the way in which we make progress is that scientists take existing equipment and they attempt to do the next stage at the cutting edge of what they're studying. They find that equipment is inadequate. They collaborate very often with the company that built the equipment to make improvements in the direction that they're going. And that piece of equipment then becomes more capable of doing a variety of other things. There's a very good back and forth between basic science and industry in terms of making progress in both. And there are also our discoveries that you have. I'll give you one example right now. With the studies that we're doing of using liquid argon to look for dark matter, we ended up working on the development of a new type of device called a silicon photomultiplier. It's a light-sensing device that makes it possible to, in a much simpler way, get more sensitivity to light. And that, combined with liquid argon, is being used to develop a new form of device for positron emission tomography, as I mentioned earlier. It increases the sensitivity to the point that you can now treat children when you couldn't before, because the amount of radioactivity you have to inject in order to then trace where the radioactivity goes in the body would have been excessive. It's now possible to use lower doses. It expands what you can do, and you can do it in real time. This is, in fact, scientists whose prime task has been basic science, but they've spun off the new capability into a technological advance. The other thing that's the case is that those 75% I mentioned of the students who started out perhaps thinking, I'm going to be a university professor, they end up in industry, a lot of them, and other cases where they're using this evidence-based decision-making. But a company that wants to be able to advance, to do the next stage in their development, has got to have its eye on the basic science that is underlying their product. And if they don't have people working for them and allowed to work for them, maintaining their excellence in that particular discipline at the cutting edge, they're not going to be able to develop that next product. We've had an example in Canada of a major national lab where the government has said, cut off all that basic science stuff you're doing. You're wasting a lot of time on that. You're going to be, quotes, a concierge for industry. The people that work in that lab are going to have contracts with industry to do A, B, C, or D. The result was, first of all, morale went to heck. They cut off the connections with universities to a substantial degree. I'll hasten to say this is all changing now. But it just didn't work. You could not have a national laboratory attempting to assist industry if that national laboratory wasn't at the forefront of the various fields that the industry is seeking expertise from them. And so it's a two-way street. The basic science and industry is valuable both in terms of keeping industry at the cutting edge and in educating people who keep industry at the cutting edge, in my experience.
Thank you very much. I think all three of you have made a very important but basic point that I think is important for us to get across in pursuing transdisciplinarity, and that is that it does not exclude basic sciences, right, or scientists who are focused on curiosity-driven research, that the imperative and the urgency of action means we have to harness the full spectrum, not only of disciplines, but of approaches, of interests and perspectives of science. So it's about meaningful, deep collaboration. And I think that has implications for funding structures. It's not your TD funding stream here and your curiosity-driven stream there. We need to find ways of integrating that. What we still then need to prove is that TD too can be fun. But we are out of time, and so that's something we should discuss over refreshments. Aldo, I hand back to you, and I thank Dr. McDonald, Mansai, Thulani very much for joining me.
Thank you very much. Heide, a delightful facilitation, style and insight, absolutely as always. And thank you very, very much, Thulani and Mansai. We're truly honored by your participation and awed by your experience and achievement and what you've added to this insightful discussion with Dr. McDonald. Heide, if you're trying to make that case for TD slightly too strong, yes, it might be fun. I'm sure it will be. But some will disagree also with the depth of complexity of Dr. McDonald's field in tagging that as fun. Two takeaways for me, not only from your lecture, Dr. McDonald, but from this insightful panel. Number one, sustained and insightful funding commitment and an enabling environment that science facilitators, funders, and agencies must create and must take forward. And secondly, that can only be done strongly and in a sustained way through adequate partnerships that are wide-ranging, that are inclusive, and certainly that are enabling. In other words, a transformative funding approach is necessary. I'm very happy that in collaboration with numerous of our partners, and the High Commissioner has mentioned this, I think we're reaching that level. And as a global funding community, using public funding for directed, excellent research, as in your case, Dr. McDonald, much of your research has been funded by public funds. I think that is that transformative environment that must be brought. I want to finish talking before I invite our co-host and principal host, of course, Professor Coupe, to the stage. But colleagues, on behalf of the National Research Foundation and also the Canadian High Commission. Thank you indeed for your participation today. Freshmen are outside, and there's a small group that have been invited to a separate lunch, which is in the main building, and the teams will lead you there. I need to really acknowledge the extraordinary leadership by Tabiso and Lerato, Jason, Kathleen, and the team, Amy, everyone who's really been extraordinary in putting this together. And I want to acknowledge the technical owner of the NRF's Science for Society lecture is Dr. Beverly DeMons right over there. She's the group executive for science engagement and stakeholder relations at the National Research Foundation, for the insightful way in which this process is managed and highly acknowledged in the country and further afield. Beverly, thank you very much. Colleagues, then, as a final word, really our pleasure to welcome to the stage Professor Tawana Kupe, the Vice-Chancellor and Principal of the University of Pretoria. Professor Kupe, you might have heard that you were thanked profusely for your co-hosting when this session started, and we really had great pleasure in working with you. Dr. McDonald, thank you indeed for your participation today. Thank you.
Thank you very much, Aldo. I had the pleasure of meeting Dr. Art McDonald at his center at Queen's University a few weeks ago. But also, what you are not aware of is that I was partially listening to your lecture because I was up in the room 5 there through your talk. So I did something which was a naughty thing to do when I was a student. When a teacher was boring, I brought in a popular novel. Normally it was James Hadley Chase. And you put it on your knees and you pretended to be listening and reading. Because I was attending another virtual meeting, but your lecture was more interesting, so I was doing that. But once or twice they caught me out, but I was listening to you. But a very good afternoon. I just wanted to say, this is very fascinating for me in relation to things that you were saying when I could now physically come into this room about transdisciplinarity. This morning I started by opening a conference right next door. And the conference is about transdisciplinary approaches to reproduction in Africa. And it's made up of scientists, people from the social sciences and humanities, and young scholars. Further down in another room is people from veterinary science doing a One Health kind of discussion on relation to animal, human, and plant health. So when we claim this to be a transdisciplinary university, it's not an empty claim. But I stand between you and wine and refreshments, so I'll be quick. Good afternoon to everyone here today. It's a privilege for me to make some closing remarks after a morning which I'm sure you will all agree has been incredibly inspiring and beneficial. Thank you to everyone who has attended and to those who have insightfully contributed both to the Q&A and the panel discussion which I attended in person and not sneaking upstairs. Our thinking has been stimulated and there is little doubt that these conversations will be carried forward with exciting outcomes further down the line. Dr. Art McDonald, thank you for your captivating us by sharing the very exciting and ambitious life journey which you have traveled. We stand in awe of what has been achieved through the courage and unshakable determinations of the Sudbury Neutrino Observatory SNO, and cannot help being anything but humbled by your brilliance. Thank you for illuminating our understanding of neutrinos and demonstrating how enormous research effort resulted in changing the laws of physics at a very basic level. By the way, I think I did say this to you. Last year, I hosted 5 Nobel Prize winners in this facility, virtually, of course. One of them was Brian Schmidt, a physicist, a Nobel Prize winner like you. But the topic was very interesting. It was the future of work, not actually physics. And so again, that transdisciplinary play on things. We also appreciate how you have shared many of the principles which accompany the road to success and how clearly you have modeled a people-centered, collaborative approach where the outcome is priced above individual acclaim and recognition of the group effort is emphasized. May we seek to follow your example as we carve out our unique paths towards trying to understand the universe in which we live more completely. The title of our panel discussing enabling Nobel quality research in Africa. You remember you asked me at the center, I said, what do you want me to talk about? Would enabling Nobel quality research be fine? Of course, I was in awe of you. I said, absolutely yes. And here we are. In a way, sums up the very road that the University of Pretoria embarked on 5 years ago to develop as an inspiring place where scientists, scholars, and students from different disciplinary backgrounds and different parts of the world meet and interact in pursuit of research that matters. During this time, the university has developed 5 new major transdisciplinary platforms, which if one of them is this, the Future Africa Institute and Campus, and then exactly a kilometer where I'm pointing, Engineering 4.0, as large as this facility without the accommodation and the drinks place, but there's a place to have drinks in there for engineering, but it was meant for civil engineering, but is now anything but civil engineering. So colleagues are collaborating from humanities department, health sciences, humanities, agriculture, and others. Then Innovation Africa at UP, which is this precinct, as you might have seen when you came through. And also, most recently, the Center for the Future of Work, which was made deliberately an outcome of the Nobel Prize dialogue that we held last year in this very facility. These platforms foster a transdisciplinary research culture across the university community and are creating a critical mass of researchers for new knowledge generation to address current and future challenges. Being positioned as a central player in the advancement of South Africa, Africa, and the world through cutting-edge innovation has guided the university's vision as set out in the 15-year blueprint UP 2025. When it was created, we thought 2025 was very far, but it's actually around the corner. And re-emphasized in our latest 5-year strategic plan, Destination 2026. You can see we have cheated and tweaked it by a year, but that's what you do in my position. The most recently released 5-year strategic plan. The implementation of all our strategic imperatives continues to be guided by the vision to be a leading research-intensive university, recognized internationally for its quality, relevance, and impact. Not just impact in the research metrics that you use. Those are absolutely important for quality. But societal impact is what we need to strive for, to bridge that gap between lack of understanding of science on the one hand and also distrust of science on the other hand in all of this new world where science and facts no longer matter to some folks. And also for developing people, creating knowledge, and making a difference locally and globally. The complexities which we face in our highly disrupted world require only the best Nobel quality solutions. These problems are too sizable to be dealt with individually, and that's I think what the panel was saying, but when tackled collectively and through partnerships which pool expertise and resources and foster learning, tangible results become achievable, and I would dare say societal impact is more possible. Through identifying and sustaining key international partners and knowledge networks, which is why I was in Canada, we have been able to strengthen our position as a continental hub and will continue to do so. As discussed, African challenges are unique and require homegrown solutions that are appropriate to solve them. And given that the future of the world depends on Africa, given its useful and fast-growing population, it is absolutely imperative that our young scientists and researchers, I mean you to learn, are provided with the environment in which they need. It is brimming with talent, and we have the responsibility to afford them the opportunity to be the best that they can be. A focused researcher has the potential to produce outstanding outputs, and there's no more critical time than now to support this focus, given that in many instances, the very livelihood of our planet and future generations depends on their success. Thank you, and refreshments will be served right now.